Okay, good. Um, so I wanted you to review activities. And activities are here in this section, solutions of electrolytes. So it's a little more than a page, the solutions of electrolytes, but we don't have to know some of this stuff here. What we want to do is we want to scroll down here. And this electronic version just blends the pages in together, so I don't have a page number for you. But in the book, there's a page. This is why I say there's one page, because it's on one page. And so you have to go down this section, and you can kind of skip over the first stuff if you don't want to read it. But basically, around the middle of section 19, or near the end of section 14.9, you have this thing that says aqueous solution have two concentrations. Here. So you're looking for that. The other thing is you could search the book for activity. Activities are talked about in chapter 13 too, I think. So we're going to, oh shoot, this doesn't search the book. This goes to, I had the same problem yesterday. There used to be a search bar for the book. I don't know what happened to it. I'm sorry? The page. This one? No.
If you search it, does it not give you the ability to click on both instead of second?
Oh, does it? Oh, maybe I did. Oh, there you go. Okay, there it is. Thank you. So in chapter 13, they talk about activities, but we haven't talked about chapter 13 yet. In Chem 1A, we don't talk about chapter 13. This is usually saved for chapter 14. And so chapter 14, we look here. 3 results of chapter 14. The first result is activities are needed instead. Instead of what? Activities were introduced in chapter 13. Well, you can go back to chapter 13 and look at the introduction of activities there. Activities are needed instead. So, however, no calculations involving solution properties are 100% accurate if stoichiometric concentrations are used. Activities, so they don't really talk about it there. In all but the most dilute solutions, composition must be in terms of activities, effective concentrations that take into account interionic forces. This is getting closer to what we want. So the quote I had didn't come up in the search. The quote I had is, aqueous solutions have two concentrations. One is called the stoichiometric concentration. The other is based on, which is based on the amount of solute, and the other is the effective concentration called the activity. So if you want to read about this is the section to focus on here. Okay. So that's in chapter 14. Okay, any other questions? Mm-hmm.
So how do we know if something is like polyvalent and what kind of polyvalent it is versus a monovalent?
How do you know what's polydentate? Is this. You know, we have different levels of looking at things. So what we want to do is, if we want to understand the properties, we can just memorize the properties. That's one. Somebody this morning said, well, how they figure it out if it's monodentate or polydentate is they memorize the table. So that's a lot. Well, it's not a lot for polydentate, because there are only how many polydentates in the table? There are only 3. If you haven't memorized, there are 2 bidentates and 1 hexadentate. The 2 bidentates were ethylene diamine oxalato, and the 1 hexadentate was ethylene diamine tetraacetate, right? And so that's not a lot. But then you're just at the kind of the observation. You know, you can be an observational chemist. You can be an experimental chemist. If you want to see if it's polydentate or not, you just mix it together and see if it forms a polydentate, a chelating agent. Is it hard to break off? Is it easy to break off? That kind of thing. But that's not what we want to do, because in chemistry, we want to minimize the amount of memorization, and we want to maximize the, you know, the amount of stuff that we can predict. And so let's see if this works for me. So the property is it polydentate or is it not polydentate? So if we're interested in this particular property, is it polydentate? Then what we would like to do is we'd like to be able to correlate this with what? We try to correlate properties with what? Structure and composition. And so this is the whole point of all this chemical reactions review stuff. This is a question I got asked earlier, you know, this morning. And that is, like, ammonia. What would you expect ammonia to be? Monodentate? Polydentate? What? Monodentate. We got this nitrogen, right? What would you expect nitrogen trifluoride to be? We got a nitrogen just like ammonia. So you'd think it'd behave just like ammonia because it kind of looks like ammonia, right? But it's not very good. In fact, we wouldn't really consider it much of a Lewis base, because why? That's true. Fluorine, you know, fluorine takes the nitrogen's electron cloud density around again. And the electron, it doesn't really, because it's still a polar covalent bond, so it doesn't completely take it off. So what we have is we have these ways of trying to visualize it, you know. One of the ways of trying to visualize it is if it did take off the electrons, you know, if fluorine did take off the electrons from nitrogen, what would the charge on nitrogen be? And that we call the oxidation state. And so from this, what I did was I talked about this, and I don't know, but you know, the oxidation state on nitrogen in ammonia is -3. The oxidation state on nitrogen in nitrogen trifluoride is +3. Totally different. So nitrogen trifluoride is not going to act as a amine. It's not going to be our typical Lewis base. Amines are weak ammonia-like bases. So what we did is we tried to do a structural analysis, because not everything's in the table. So if nitrogen trifluoride's not in the table, then what do? Well, You could say, well, it wasn't in the table. We get this type of thing asked. When I was a student at UCLA, initially, a lot of the people I transferred in there said, that wasn't fair. That wasn't in the lecture. That wasn't in the homework. But quickly, like a couple of quarters later, nobody says that because everything's not in the homework and everything's not in the lecture. It's like, it's to be expected, It's not going to be like your homework, and it's not going to be like lecture material. It's going to be something completely out. Well, if it's something completely out, then how do you figure out what to do? Well, you start thinking, like, if it's a structural problem like this, or properties problem, then you start trying to correlate it with structure and composition so you can kind of figure out what it is. And so, they're going to throw in stuff. They're going to throw in ligands there. If this were Chem 1B at UCSB or UCLA, they're going to throw in ligands that nobody's ever seen, and that's to be expected. They're going to do that, and so that's why I was prepared for that. I was prepared for that by trying to understand it as much as I could in terms of composition and structure, so I could try to guess or predict what should happen. And so if it's on the table, great. But what if it's not on the table? What if it's not on the table, then we do. And so I gave you an example. Some people told me, well, there's only bidentate and polydentate. Well, what does poly? Poly means it could be anything. So we could have something like this. And so this was the example I gave in class. The example I gave in class was this. So I used this example this morning for just a question during office. This is an example of a tridentate ligand. So this would be like a question you might get. Here, this would be it looks like a bidentate because it looks like an ethylene diamine, but this is like a diethylene triamine. Do you see that? Kind of two ethylenes sandwiched between three amines. And so kind of like a diethylene triamine type. This has a systematic name too, but systematic name for this is complicated because you got two carbons here, two carbons there, they're attached. And so in organic chemistry, you have all these rules for systematically naming these things, and those rules would get quite complicated quite quickly. So sometimes what you'd say is, okay, we have an ethylene diamine that's attached to an ethylene diamine kind of thing, but one of the nitrogens are not attached. But anyway, this would be an example of a tridentate because here you could easily see it could be bidentate, like ethylene diamine. But now we have this other arm hanging there. This other arm's bored. It wants to do something. It wants to attack something because it's a base. This is a base. If I threw two fluorines on there, would it be a very good base? Probably not, but there's a carbon on there, and I could change things as far as that goes. But if this wants to attack something, well, it can attack that metal, and then it would be a tridentate ligand. And so you would do it based on structure and composition. That's how you would determine it. So we'd see how it is. All right? So this is the example I did in class. Okay. Well, moving on here. Then. Were there any other questions? No. All right, so after two failed attempts at coming up with a pattern for this set of experiments that we looked at with the copper 2 and the tin 2 reaction, we finally come up with a pattern, and this pattern works. This pattern works not only for the copper 2 plus tin 2 reaction, but it works for all the reactions that were observed. And we're going to just come up with a generic reaction here. Here are the reactants, here are the products over here, this generic reaction. And what was the pattern that turned out to work for all of these? The mole ratio didn't work. If you didn't see the videos, I'll give you the spoiler version. The spoiler version is the mole ratio didn't work. Then we went to the molarity ratio. The molarity ratio worked. I mean, the mole ratio, actually, let me back up. The mole ratio worked only when the number of moles, only when the units canceled out. And so, for example, I had moles cubed on the top and moles cubed on the bottom. When the units canceled out, but when the units don't cancel out, let's say I have moles cubed on the top and moles squared on the bottom, then the mole ratio doesn't work. Okay, that's in the video. You can take a look. And so the mole ratio worked for the copper-tin reaction, but didn't work for many other reactions. And therefore, it wasn't a good pattern, unless you want to memorize specific patterns for specific reactions, which we don't, if possible. Then we went to the molarity ratio. The molarity ratio works for a broad swath, but it deviates a little bit. It deviated a little bit for concentrated solutions or high pressure gases. And so it had to be modified a little bit. And the modification comes like this. This is the equilibrium law. So make sure to look at those videos if you haven't. K is a constant, and it follows a pattern, and the pattern is that the activity of the products, Ag to the G, AH to the H, dot, 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 over the activity of the reactants, AA to little a, AB to little b, dot, 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 is a constant. And we call this KEQ, the equilibrium constant. And that's what it is. This is where the activity is the effective concentration or the effective pressure. For solutions. Or the effective pressure for gases. When I talk about effective pressure, this is the like what we call the real pressure. Versus ideal. And the effective concentration for solutions is close to the molar concentration, and the effective pressure is close to the ideal pressure. And so this final iteration of the pattern here can be pretty good, depends, or it can be a little off. if we use these ideal values rather than the real values. And so the way I think about it is like this. When we calculate the properties of gases, we use the ideal gas law, like 99.9% of the time, right? Because it's just a lot easier. And we just assume that, well, if it deviates, we're going to have some error. And we probably should use the van der Waals equation, but we aren't because it's just too much work. Activities are beyond the scope of Chem 1B.
So will they just be given usually then?
They aren't even going to be given. They're beyond the scope of Chem 1B, so for Chem 1B, we're just going to assume everything's going to behave ideally. We will assume ideal behavior. What that means is this. For high concentration or high charge, and or high charge, I should say, and or high charge, then expect errors. And the error is going to grow in magnitude the higher the concentration and the higher the charge is. This is like if we use the ideal gas law to calculate the pressure of steam at 0 degrees C, 273 Kelvin, is it going to give us an accurate pressure? No. I mean, we are going to expect it's going to fail completely, right? And so the same thing here. If you're dealing with high charged species or high concentrations, then we're going to expect some kind of failure here. But hopefully, most things behave. And so most things are going to behave as long as we don't keep the concentrations very high. And so what we're going to do is we're going to try to use lower concentrations here. So if we're dealing with, let's say, 16 molar stuff, then 16 molar is kind of high concentration, you know. But instead of dealing with 16 molar, maybe we go to 0.1 molar. 0.1 molar is kind of low, and the lower the better, right? And so even though 0.1 molar seems so dilute, which it is, well, that's kind of our standard concentration. A lot of these problems we do at 0.1 molar, and you might think, why so small? Why so small is because we don't want a huge error in there because it kind of makes the calculation less meaningful, you know. And so we're kind of artificially limiting ourselves there. Now, if we get a high concentration, then probably best not to use the stoichiometric concentration. It's probably best to use the activity or the real concentration. And that we need activity coefficients, and we need to do a little bit more math. But in Chem 1B, we don't spend the time. In the next, if you take thermodynamics, then you're going to be using activities. And they aren't hard. It's not hard to do. It's just more than what we're going to do. It's like if you had to use the van der Waals equation for every single gas calculation, it's not hard to do. You could do it, except for solving for V. Solving for V is hard to do. Most people solve for V. You know the van der Waals equation? The algebra in that? Most people solve for V using the method of successive approximations. Did you see the method of successive approximations in the video from yesterday? Yes, maybe none. Yeah. It's the guess and check method. So we do it there. And so solving for V using the ideal gas loss algebra is pretty straightforward. But solving for V using the van der Waals equation, let's take a look at that really quick.
So would you consider everything over 1 molar high concentration?
Yeah, kind of high. Even 1 molar is starting to get higher. At 1 molar, we're going to expect more deviations from. I'll show you some examples here. You know what the most ideal gas is? The most ideal gas of all gases is helium. And helium even deviates from ideal behavior. And so even with helium, we expect an error. But the error is just 5 parts out of 1,000, 0.5% error. It's not huge. 0.5% error, we'll live with it. Right? But as we get to other gases, like something like SF6, we're looking at more like a 12% error. It's starting to get bigger and bigger, the error.
Can you scroll up real quick? Like N2 isn't it technically closer? It's only 0.002 off versus the other one, which is like 0.005.
Yeah.
Does that mean N2 is actually more ideal?
Well, you have to look at the range, of scenarios, because we're only looking at one temperature here, 0. But when you look at all the range of temperatures, then N2 is a lot less ideal. Number one, as you cool down N2, eventually it liquefies, just like steam. Steam will liquefy at 100 degrees C. N2 liquefies, but it liquefies at a much lower temperature, like minus 190 degrees C. At minus 190 degrees C, then it's no longer a gas. And so the ideal gas law fails there. Whereas if you look at helium and you cool it down, helium stays a gas all the way to 4 Kelvin. At 4 Kelvin, which is minus 269 C, then it liquefies there. So helium stays a gas at a much wider range, therefore we call it more ideal. And then when we look at the deviations, this is only 1 point. What we have to do is we have to look at the deviation over many points. Many points being the temperature, and then we look at the deviation, because it's like, a broken clock, they say, is correct, right, twice a day. Well, it's the same thing. At 1 point, one gas might be better, but when we look at the behavior as a whole, this is the behavior as a whole. So we might say, well, all the gases are pretty ideal. At 0 pressure, close to 0 pressure, all gases are ideal. And so you might say that oxygen, hydrogen, and CO2 are equally ideal at close to 0 atmospheres, point whatever, microatmospheres or nanoatmospheres that you're at. But when we look at the whole range here, yeah, it's going to vary, Like here, wow, O2 behaves perfectly ideal under these conditions, right? But it's not so ideal. And, this is O2, sorry. CO2 behaves ideal here. O2 behaves ideal here, and so it varies. So that's what I'm saying, when we look at the entire range. So anyway, we don't want to use the van der Waals equation. If you use the van der Waals equation, this is what we call, solving for P is easy, because it's first order in P. Solving for V is a pain in the butt. And solving for V it's a cubic, because what we do is we multiply by V squared to get V out of the denominator. When we multiply by V squared, then we have a V cubed term. Are you good at solving cubic equations algebraically? So normally what we do is, okay, we get a V cubed, then we get it in cubic form. A V cubed plus B V squared plus C V plus D is equal to 0. And then if you have that, my calculator can do this. I have a Casio that solves both quadratic and cubic equations. And so all I do is I plug in A, B, C, and D. and then it gives me all the x's, right? So I could do this, but there's a lot of algebra, and if I were to do this, I wouldn't even get it into cubic form because I think getting into cubic form would take me too much time. And so what I do is I just use the method of successive approximations so I don't have to get it into cubic form. I'll just go ahead and do it via the method of successive approximations. So in Chem 1A, Chem 1A last semester I didn't assign it. Normally in Chem 1A I assign a problem where people have to solve this equation for V. And the way you solve this equation for V is you use the method of successive approximations in Appendix A. That's the easiest, I think, rather than getting into cubic form and solving for V. Oh, was it in the homework last semester?
Very second one.
Okay, then good. I assigned it. Maybe I switched. Eventually I switched to all tutorial problems, I thought.
Yeah.
But yeah, this is a good problem because this is the first use of method of successive approximations in Chem 1A, our order. And so if you go back to the video, we had to use the method of successive approximations, and you just keep guessing and guessing until you get it. But we don't want to use this because this is a pain. So what we're going to do is we're going to live with the error. How big is the error going to be? Well, the error might be small, or the error might be big, And so we're just going to use the ideal gas law because it's so much easier. I mean, solving for V takes you, what, an hour, a couple of hours to solve for V, something like that? 30 minutes, 10 minutes. Depends on how lucky you get with the guesses. If you're very lucky with your guesses, you might get in 10 minutes, something like that. But if you're very unlucky, it could take you hours to get it. I remember seeing on a test, and I felt sorry for the student, but on the test, I gave a method of successive approximations problem on the test, Chem 1B, and they were guessing, and they had 5 pages of guesses. They had 5 pages of guesses. They were there for, I don't know, they were there well after. But they had like 5, and they still didn't get the answer. But they could have gotten it. Maybe if I gave them another hour or 2 hours, they might have gotten it, by just guessing and checking, But anyway, it takes. So what we're going to do is we're going to just call everything ideal, right? We call everything ideal, assume everything's ideal, but we know if we're going to do a calculation with something like SF6 or H2O, that's going to yield a bigger error. And so I can't have as much confidence in my answer versus helium. If I did helium, I have a lot of confidence. Or nitrogen or oxygen, I have a lot of confidence in the answer. Does that make sense? And so we're going to do the same thing here. We're going to treat everything as if it were ideal, but if you know something's going to deviate from ideal, I'm not going to have as much confidence in my final answer as I would for other scenarios. So we can easily give an example of this here from chapter 14. I'm going to treat everything as ideal in chapter 14. So soluble salts in Chem 1A, I say soluble salts are strong electrolytes. What do strong electrolytes do? They ionize or dissociate completely. So if I have sodium chloride is a soluble salt. Group 1 salts are all soluble. Sodium, potassium, lithium. And that's going to ionize completely. When it ionizes completely, it's going to break up into how many particles? 2. A sodium ion and a chloride ion. And so that's ideal. Ideally, it breaks up into 2, right? So we're just going to say breaks up into 2. Magnesium sulfate, same thing. It's a strong electrolyte. Sulfate is covalently bonded oxygen, so those oxygens don't come off. If it's covalently bonded, it's going to stay. So how many ions does this break up into? 2. Magnesium ion and sulfate ion. And ideally, that's 2. And then lead 2 nitrate should break up into how many ions? 3. 1 lead, 2 nitrate. 3, right? And so we're going to treat everything as ideal. However, the error that you expect in the calculation will be the same for all these or worse for... Which one do you think the error is going to be worse for? We're going to treat all these as ideal. However, in the back of our mind, you know, so for example, magnesium sulfate has a huge deviation from ideal behavior. Do you see that? Because this should be 2, but we're getting 1. Whereas sodium chloride, is that a huge deviation? No, I mean 10%. Okay, yeah, kind of 10%, like, well, it looks like 20%, but 10 out of 100, say 20 out of 200. So this is like 10% error? Okay, 10% error, okay. 10% error is going to save us from doing the work of something like the van der Waals equation, right? And then we can live with it. It's not perfect, but it's a lot better than spending hours doing the calculation, right? It's a compromise. However, if you do magnesium sulfate, how good is your calculation going to be? You're telling somebody you're going to get 2, but they only end up with? Well, they only end up with 1. Are they going to be very happy? No. And so here it's going to deviate more. But look at magnesium sulfate won't be so bad if we look over here. Now what is this? Well, magnesium sulfate will only give us a 10% error if we go down to 0.001 molar, 1 millimolar. Is 1 millimolar very much? No, but and you know, okay, I'm going to make you some lemonade. I'm going to make you 1 millimolar lemonade. Are you even going to be able to taste it? Probably not. It's going to taste like water, and you go, I want to return it, you know. But it's good for us because the lower the concentration, the more ideal the solution behaves. Right? And so our calculations are going to be good if we go low concentration, or if we're not dealing with highly charged ions. Then our calculations are looking okay. But the more we deviate from ideal behavior, the worse our calculations are going to be. It's the same thing with gases. The more you deviate from ideal conditions, what are ideal conditions? Ideal conditions for gases are high temperature. High temperature is high kinetic energy, and they can't interact so much. And low pressure. Low pressure means they're spread out, far apart from each other. And so if we do calculations at high temperature and low pressure, I don't worry about the ideal gas. You know, I expect the error to be kind of small, you know. But if I do high temperatures and let's say high pressures, I start to worry, you know. Or I do low temperature and low pressure, I start to worry, you know. Or the worst scenario, the biggest error would be when I have cases of low temperature, the gas particles can stick to one another, and high pressure, you know, then I expect the biggest error. And so what we do in science is this. In science, people don't care what the number is. What they care about is, you know, how much confidence can they have in that number? What does that number mean? You know, and so the ultimate, and this becomes more and more important as you go along. There's a very famous quote from a very famous physicist, and I should bring it up one time, but this very famous quote from this very famous physicist said, you know, I don't remember the exact quote, but it's like the numbers are meaningless unless you can put some kind of meaning to them. You know? And so that's part of it. So we're not going to worry about activities, but then does that mean you can completely ignore activities? No. You have to understand activities to the point where you can say high confidence, low confidence in my calculation. Does that make sense? So this is the whole reason I've been going through activities. The whole reason I've been going through activities is so that you can think in the back of your mind, well, this calculation is going to suck because, you know, the conditions aren't good. And we're making an assumption. We're making an assumption of ideal behavior, but it's going to be nowhere near ideal behavior. I remember, did I tell you about benzoic acid dimerization? Did I talk about that in this class or in the morning class? Probably the morning class, yeah. Yeah, the calculations usually suck for benzoic acid solutions if you assume ideal behavior. Let me tell you why. This was a question in at UCSB in general chemistry, and not many students got it. The professor never talked about it, and so that was a big complaint. Because I was a teaching assistant there, and so one of the big complaints was, oh, the professor never talked about this. But then I thought, okay, pretty soon they're going to learn that everything's like that, In fact, they try to make it purposely like that. They don't want it to be. They want it to be different. But let's do this.
So how do you prepare for exams like that? Do you just try and see more examples in the book?
Exactly. I try to see more examples in the book. So how because this is something I learned when I was at UCLA, was how do you prepare for something like that? Sometimes it is something out of the book, but most of the time, let me tell you, most of the time when it was something new like that, it was like one step or one additional thing, and so it was like bringing two things together, so it wasn't that hard. Sometimes it was just really hard. Sometimes they put the same problem over and over and see if somebody can get it. Eventually, out of how many years somebody might be able to get it. That kind of thing. But how you do it is you try to see. And this brings up the forest and the tree analogy. Are you going to be able to, let's say you're out in the forest and you want to understand the trees or the fauna or the plants in the forest, are you going to spend all your time just looking at one tree? And you'll know that tree very well. Okay, if that problem comes on the test, I'll be able to handle it, right? But no, what the professor is going to do is they're going to grab another tree in the forest. This is a completely different tree, but you've never seen it before. And so the best thing is to see as many trees as possible. That way there are no surprises, and that's what I like to do. And so the best way to prepare for me, when I was a student, is to do every single problem in the book. Now you go, how is it possible to do every single problem in the book? Well, this wasn't my idea. This idea came from the student sitting next to me, because I remember taking thermodynamics, and the student next to me got the high score on the test. And I got, I think, like a D or something like that, and this student got like an A+. I'm thinking, man, and I studied every single minute I had available, because this was my first quarter at UCLA. So my first quarter at UCLA, I was taking thermo, which is is known to be one of the hardest classes to take. And I might have mentioned this before, but they actually have a bumper sticker, at the bookstore saying, I passed Chem, which is thermodynamics. I didn't buy one, but I thought I was going to fail Chem. So I had the midterm, and you have a midterm and a final. And sometimes they're weighted 50-50, sometimes 2/3 final, 1/3 midterm, or sometimes you can say, okay, if something happened to me on the midterm, I want 100% of my grade. It's like going to Vegas. I want 100% of my grade on the final, and you're going to risk it. Because if you blow the final, that's bad, right? So it's okay, because I pulled out of my nosedive. I was in a complete nosedive, and I thought, oh man, I'm going to fail this class. And then I pulled out of it, fortunately, and did okay. So it balanced out. I did okay in the class. Not great, because it would have been nice to do well on the midterm, but I did fine on the final. But how did I pull out of the nosedive? Well, then I thought, I look at my score, I looked at my neighbor's score, and I thought, wow, what's going on here? Because I'm spending 100% of my time. I can't spend any more time. I have no more time to spend. And so either I'm going to change my major or do something. And then I figured, well, the problem is not the time. The problem was how I was studying. I wasn't preparing myself for the types of questions that could be asked. And so this person did every single problem. But how can you do every single problem? Because I thought that's impossible for me, because I would spend an hour, 2 hours on one problem. And then I thought, okay, so the first thing I did was whenever I spent excessive time on a problem, I didn't. I just went straight to the solutions manual. And this is the great thing about UCLA. UCLA, at least for every single class I had at UCLA, they had the complete solutions guide available. And so they just had the answer book. And so I just looked at the answer. And then a lot of people say, well, don't do that. When you look at the answer, you're hurting yourself. But no, it wasn't hurting me. What I did was then I made up for it. I made up for it by looking at every single problem. So what I did was I read the problem and then read the answer for every single problem. And then I knew if anything came out of the book or anything similar to the book came, then I was prepared because I saw every single variation of every single problem in the book. And so then I thought, those are give me points, give me 100% of the points. Easy. And then the more advanced problems were just simple variations of all those, because in the homework they try to hit all the, different scenarios. They try to make the homework interesting. And also they make it a point because a lot of instructors won't adopt a book unless they have, their favorite way of doing a particular problem in there. And so there are very few, after doing that, there are very few surprises on the test. But the only way you can do that is if you have the complete solutions guide. Otherwise, you're going to spend way too much time, which you can't. But the complete solutions guide is easy to get. There's a copy of the complete solutions guide in the bookstore. I saw one copy on the bottom shelf.
Speaking of exams, are you going to be going over the homework?
On Monday.
On Monday. I've got a couple questions about some of the questions on the exam. Would you be able to go over those today, or?
If everybody turns it in, yeah, then I could go over it. But I need to still cover some stuff. I need to finish up 16 and then start 17 today. Or you could watch the video from this morning and I can talk about the test so I don't fall too far behind. What's your preference? Well, you could watch the video at the end. It's not watching the entire. You just watch the video until we're caught up, and then you can go from there. Because I got into chapter 17 this morning.
Personally, I would like to go over the practice exam because I think it would help with understanding what might be on the test on Monday.
Mm-hmm. Okay, we could do that.
I mean, everyone else.
I agree.
All right, we'll do that then. Yeah, but if I'm going to go over it, can you turn it in? Because I want to get a snapshot of how people are doing.
Oops, sorry.
Scantron. Oh.
I missed yesterday because I was scheduling issue. What I do want to try to say again,
This is only worth 5 points, so we can make up some points later. I'll give you something to make that. All right, so let's take a look at this. Now, I mentioned that let me tell you why I cover chemical reactions at the beginning. Why I cover chemical reactions at the beginning is try to help you minimize the amount of memorization you have to do by trying to introduce like composition and structural factors into properties, like the properties of ligands. And so obviously the table of ligands, might as well record this here. The table of ligands is not comprehensive. And so when I was thinking, well, I'll throw in some ligands. I already threw in some ligands that weren't on the table. Did you guys see that on there? And so maybe we'll take a look at those first. the ligands that were not on the table. And this was very common. Like when I was a teaching assistant, actually, when I was a teaching assistant at UCSB, this is very common. They'll throw in ligands there that nobody's seen before. And also amines that nobody. I remember one test that they threw in this crazy amine on there. This crazy amine was huge. And so a lot of people got intimidated by that because they saw this gigantic amine. But there was only one nitrogen on that amine. So it behaved just like ammonia. But, I would say like a good percentage of the class wasn't able to answer that question because they didn't recognize it was just like ammonia. But it had such a crazy formula that, how could it be like ammonia?
Will the exam have a similar multiple choice to free response ratio as this one?
Yeah, kind of. No, this one has a lot more multiple choice. Our tests will have a lot fewer multiple choice. And each multiple choice will be worth more, and the free response will be worth more. This whole thing's only worth 5 points, so it's not much risk in that. But one of the things you want to know, oh yeah, let me get this before it's done. One of the things they'll throw in there are things that are not amines. Can you recognize what's not an amine? So, is that an amine? No, that's not amine, but this is nitrite, and that could be a ligand too. But nitrite, could it be? So what we do is, let's say, I don't want to memorize the table either. I want to try to minimize the amount of memorization that we do. So let's say I had no idea what nitrite's behavior was. And so if I had no idea what nitrite's behavior was, then I'd start to try to analyze it structurally. I have the composition there. Composition is the formula, so we need the formula. And the formula is going to tell us, is it molecular? What types of structures do we have? We have molecular structures. We have could be molecular, could be atomic, atoms, like helium, atoms. It could be ionic. If it's ionic, what type of structure does it adopt? A lattice, ionic lattice, yeah. And so, to understand, like, say, calcium oxide, if I had calcium oxide, we'd draw a lattice of it, alternating cation, anion. We'll talk more about that as we go along. Or it could be another type of lattice. We have ionic lattices and we have covalent lattices. Right? Covalent lattices, and then there are properties associated with that. So, for example, the common thing is if we compare CO2 versus SiO2. If we look at CO2, carbon is in the group 4 or 14. Silicon is in the same family. And so we know what CO2 is. CO2 forms molecules like this. And so you would expect SiO2 to do the same. So this is what we'd predict. But this is where we need the two-pronged approach. The two-pronged approach is it isn't all theory. There is some factual evidence we need. And SiO2 is not a gas, and it doesn't form SiO2 molecules. SiO2 forms a covalent lattice. Etc. And so SiO2 has totally different properties than CO2 because of its structure. Right. This SiO2 we call quartz, and CO2 is just carbon dioxide. For some things, we can try to start figuring out properties. So quartz, people call this silicon dioxide too. Or they call it silicon Roman numeral 4 oxide. Here. Silicon is kind of borderline. So we can use the rules for metal, non-metal, ionic compounds, or we can use the rules for non-metals. Silicon is a semi-metal. So either of those names is fine. But sometimes we even do this for molecular compounds. Even though this is not very common, both these names are quite common for quartz. For CO2, some people call it this. Another name for CO2 would be, do you know?
It's like carbon-4 oxide.
Carbon-4 oxide. Yeah, we name it like an ionic compound. And so this is quite common too. Carbon, Roman numeral 4 oxide.
So despite the fact that it's a gas, it can still be
It's well, no, they just name it that, but it's not ionic at all. You know, this is the name for ionic compound, but it's molecular, and its properties are going to be totally different.
Why does carbon dioxide have a gaseous form but not silicon dioxide?
That's a good question. Why? And then what we need is some kind of fundamental, kind of description of what's going on with that. And the fundamental description of what's going on would be what? Fundamental description that can make predictions, like it would be the theory. And so we need a better understanding of the theory. But right now we're just, the theory, the problem with the theory is it becomes quite complicated. Because what is the theory that underlies chemistry? Quantum mechanics. And the quantum mechanical calculations, we should be able to figure out based on the quantum mechanics. Based on the quantum mechanics, we can figure out that structurally, a quartz structure like this with a network covalent lattice should be lower thermodynamically in energy than a CO2 molecular structure. And there we can do the calculation, because what structure we find in nature should be the most stable of it. Are diamonds very common? No, but coal is, and graphite is, but diamonds aren't very common.
They're more common than you think.
Yeah, that's true. Diamonds are more common than you think, but still not that common. I'd like to find some of those diamonds.
Can you say something that like diamond technically slowly becomes like graphite or something like that?
Yeah. But it's so slow, you're gonna die before it happens. I mean, unless that guy don't die. There's a seminar, but there's a professor at Harvard. Heard of him? He wrote a book. He came up with a theory of aging. It's the information theory of aging. And theories usually have some support. And so there's some support for that. But there's got to be a lot of evidence in support of it. Anyway, getting back to this, why is it? Well, there's got to be some kind of structural reason. It's got to be because it's more stable in this form than it is in that form. Now, what we need is a theory to give us a more fundamental description, because that's just purely observational. It's purely observational. This is the form we find in nature. That's it. I wish I had that for you, but I don't. I don't have a nice simple answer, because it's kind of complicated, because I would think it's this. I would have thought it's that, personally. And so this is why we need the two-pronged approach. We can't do everything with theory, right? Because it would be too complicated to calculate, and the calculation should show that this is more stable. You know, it's the same thing. Which is more stable? The graphite form of carbon or the diamond form of carbon? The diamond form of carbon adopts the same structure, except rather than having silicon and oxygens, you make a lattice of carbon atoms only. It's kind of the same structure, not exactly the same. Which one's more stable? A lattice of sp3 carbons or a lattice of sp2 carbons? Turns out a lattice of sp3 carbons is more stable. No, it's not. A lattice of sp2 carbons. Why is that? Well, this is part of the, this is some things we just have to memorize to understand, and later on we'll get, or try to figure out the theoretical reasons for that. And so we need some, we can't get rid of memorization. We need some memorization to help us understand these things deeper. But getting back to this, we analyze it structurally. So if I've never seen nitrite before, I might think that this is a tridentate ligand as well. I just did one tridentate ligand, and this looks to me like another tridentate ligand. Now, I know that there are two resonance forms for this, right? And so the first thing we do is we choose one of the resonance forms. This is a false choice because, neither of these is correct. What is the correct structure? The hybrid. But we're not going to get into it that deep. What we're going to do is we're going to choose one resonance form. Let's choose this resonance form here. Out of these three, which one do you think is going to be the best base? So I'm just going to freeze this structure. We're going to use this. It doesn't alternate between them, but we'll just use this structure. Out of these three, which one do you think is going to be the best base? Oxygen or nitrogen? If it's oxygen, then which oxygen would be better? The one with the negative charge here. That should be better. However, that's because I called bases are negative, right? Acids are positive. That's just to the simplest, if you were to boil down quantum mechanics into something very simple, quantum mechanics would boil down to Coulomb's law. What is Coulomb's law? Coulomb's law is opposite charges attract, like charges repel. The reason why Coulomb's law exploded into quantum mechanics is because when we look at negative charge, it's a negative charge cloud, electron cloud. And how are these clouds distributed around the atoms? We have orbitals and that type of stuff. So when you start including all the orbital stuff, and then how do orbitals interact? Do orbitals just overlap? Overlapping orbitals we call what theory? We call valence bond theory. However, if we take those orbitals and then combine them, LCAO. LCAO stands for what? Linear combinations of atomic orbitals. Then we get new orbitals called molecular orbitals. And so if you recall, orbitals are wave functions, and so we could have a wave. If we have a wave like this, like an s orbital has a wave like this. Well, that's what we call positive amplitude. But could the s orbital also be negative amplitude? Yeah, just flip it upside down. It's negative amplitude. So if we take a positive amplitude and do LCAO, we get a bonding molecular orbital. If we take one that's wave up and the other s orbitals wave down, then we get positive and negative, and that becomes a antibonding. That becomes destructive interference. Remember, constructive and destructive interference. So we have all that. And so to the first approximation, this is called the first approximation because this is looking at everything through a lens of Coulomb's law. Then, of course, this oxygen's the best, right? But then you go, well, nitrogen's typically better, than oxygen donors. And so this nitrogen may attack first. In fact, we kind of expect that nitrogen to attack, but you're going, that nitrogen's going to have a positive oxidation state. What's the oxidation state on that nitrogen? It's +3, like NF3. But then there are other factors that we consider. The other factors we consider are the orbitals, how the orbitals interact. And so it becomes more complicated. So what we're trying to simplify things. But in the back of our mind, we have to realize that things can be more complicated than what we think. And so this could be a tridentate. So let's go ahead and show how this can be tridentate. So I'll put a metal here. And we're going to attack it here. That's one. And then you remember what if we have a single bond, single bonds are free to rotate. So I'm just going to rotate the lone pair down and attack here. Are double bonds free to rotate? No, but no big deal. I'll just take this lone pair because they're one lone pair on one side and one lone pair on the other. So is this a tridentate? Could this possibly be a tridentate? And so what we do is we say, well, if it's tridentate, what would it form? And so what we'd form is this. I had rotated this lone pair so it comes down here. Now that has no lone pair. And then I'm going to try to keep the oxygen like this and then have one lone pair bond there. That's going to leave one lone pair out there. And so I have a tridentate. That looks like a great tridentate ligand. Remember why bonds form? Why bonds and molecules form is because of stability. The more bonds we can form, the better. But this does not look feasible. This does not look feasible because it's not even a four. It is a four-part ring here. And so if we look at the N-O-N-O-N-M, that's a four-membered ring here. But we also have this. What is this? That's a three-membered ring. And then we have another three-membered ring. And for geologists would recognize, or may recognize this. You know what this looks like to me? This looks like a tetrahedron. Tetrahedron is two three-membered rings and one four-membered ring. Is that right? Yeah, something like that. Kind of, there's no bond there. It's just showing the proximity to it. Anyway, something like that. But there's no way this is going to happen because of the ring strain. So could it be bidentate? Well, if it were bidentate, let's just knock off this nitrogen here. Could it be bidentate? So I'm going to knock off this nitrogen and make that a lone pair here. Is bidentate possible? No, this is a four-membered ring. 1, 2, 3, 4. The bond angles in a four-membered ring are 90 degrees. Too much strain, bond strain. It's not to say three-membered rings and four-membered rings don't form. 3-membered rings and 4-membered rings do form. And you have to be very careful because usually those end up exploding. And if they explode, then you can lose fingers or die potentially even. And so there are a lot of, there's, one of the laboratories at UCLA is located on the roof of the chemistry building. And that way, if they have an explosion, they can isolate it to the roof and they don't have to evacuate the entire floor. And so that's the explosives lab, UCLA, or the high energy chemicals. People try to make these. 3-membered rings are called epoxides. 4-membered rings can form. These are in organic chemistry. And they use these reactive chemicals to make interesting compounds. And so a lot of people want to make these as precursors to interesting things.
So are the 3-membered rings more explosive or reactive?
Yeah, than 4-membered rings. So that means nitrite should be a monodentate ligand. And nitrite, oddly enough, you'd think this nitrogen is not very good, but this nitrogen is very good at binding. And one of the things that helps, so this, if we look at the charge, there's a formal charge on this usually, but in organic chemistry, when we add this is called a nitro group in organic chemistry, when we add that creates a formal charge. And so in organic chemistry, we see nitro groups here. And typically in nitro groups in organic chemistry are written like this. So if there's a nitro group in organic chemistry, we'd have a negative charge on this here, but the nitrogen has what charge? The nitrogen would have a positive charge, and there'd be resonance here. And that resonance will help stabilize that. Now, when we look at transition metal complexes, if I have a nitrito N, am I going to put a positive formal charge on the nitrogen? No. And I'm not going to change the charge on this. And so this is one of the big differences here. If you go on to Chem 7A, you're going to write it like this. But in Chem 1B, we're going to just keep writing it like this, as if nothing changed. Nitrate's still -1 altogether, and the metal's still +X. That's because we count it wrong in Chem 1B, because we should be using MO theory for this. So actually, I need to go back up here to this. Sulfato, that's sulfate, right? And so you have two choices here. You could look it up in the book. This is open book, open notes. Or you can analyze it structurally. Let's say, you didn't memorize the table in the book. Is sulfate going to be a monodentate or bidentate ligand? Now, when we do sulfate, there are two ways that it's traditionally written, the Lewis structure. The most common way that sulfate Lewis structure is written is 2 double bonds, 2 single bonds. Negative formal charge in this oxygen, negative formal charge in that oxygen. And the reason that this is good is because the formal charges have been minimized here. Or also in Chem 1B, we could have written it this way. But this way, we get negative formal charges in all the oxygens, and the sulfur ends up getting a +2 formal charge. +2 formal charge is considered a high formal charge. And so people are saying that this is not stable because of the +2 formal charge in sulfur. So what we're going to do is we're going to expand the octet, brings sulfur's formal charge to 0. Quantum mechanical calculations, fairly recent quantum mechanical calculations show which structure to be more accurate. The first one? This is at the end of chapter 11. At the end of chapter 11, it's the second one. It's more accurate, but anyway, it doesn't matter. What we're going to do is, even though these oxygens are in reality all the same, because we have resonance forms for this. How many resonance forms can we draw for this? A lot. And then we're going to have the resonance hybrid, right? But what we're going to do is we're going to either take this structure, the left or the right, and then say, could sulfate be a tetradentate ligand? Then we go, well, sulfur, what is the geometry around sulfur? Yeah, it's going to be sp3. It's going to be tetrahedral. Right? And so could it be tetradentate? No. Could it be bidentate? Possibly. This could be bidentate, but automatically you probably could eliminate it being bidentate. You know, we could either do it with this first structure, which is potentially not correct, because this first structure requires d orbital participation in it. This is going to be sp3 hybridized sulfur. sp3 you can only fit an octet because you have 4 sp3 orbitals. 4 sp3 orbitals is 2, 4, 6, 8, 8 max electrons. We have 10 electrons here. Actually, 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8, 10, 12 electrons here. We have 12 electrons here. We fill up all sp3 orbitals. Where are the extra 4 electrons going to go? Well, what's next? We've used up all the p's. We could go to the s, but the s are going to be the 4s or the 5s. 1, 2, 3, 4s. We have to go into the 3ds. And so this requires d orbital participation. This is what's reason. But anyway, this is, could this be bidentate? It wouldn't be this oxygen, it would be this oxygen. But sp3, all sites are the same. So even though that looks, why are you taking the two that are opposite? They aren't opposite. All sites are adjacent to one another. There's no opposite in tetrahedral. And so we take those two. Could it be bidentate? No, it's got to be monodentate. Oxalato, we talked about that. That's bidentate. Complexes form as a result of a Lewis acid-base reaction. Is true or false? That's true. Select all ligands that are bidentate. So B, what's the name for B? Can somebody tell me the name? It's not ethylene. Ethylene's 2 carbons. How many carbons do I have here? 1, 2, 3, 4 carbons. Propylene's 3 carbons. I have 4 carbons. No, there's no tetra. It's called bute. Bute is 4. And so this would be butylene diamine. Butylene diamine, is that okay? This is okay because if I have a metal there, I'd go metal and then nitrogen. That's 1, 2, 3, 4, 5, 6, 7. That would be a 7-membered ring. No problem. 7-member ring, no strain. How about this? This is called methylene diamine. Is methylene diamine okay for bidentate? No, 4-membered ring, not okay. EDTA, 6-membered ring. 6 coordination number of 6. In those 6, it forms a whole bunch of 5-membered rings. Oxalate? Yes, so just B and E. Iron has a coordination number of 6. Lead has a coordination number of 6. When we deal with the coordination number, these sodiums are outside the coordination sphere. And so just the EDTA is coordinated. Chromium has a coordination number of 6. These are bidentate ligands, so each of them bites 2 places. So it's 6. The oxidation state of nickel, 0. It's weird, but it's 0. It's a neutral metal. And I think this is how you do the. Did I ask you how we do Roman numerals of 0?
Does not exist.
I think this might be correct. I don't know. But the oxidation state is 0. Write the name for this. So tell me the name. Disodium or sodium? Sodium. And that's a cation. And the anion is called ethylene diamine tetraacetato. Unfortunately, you have to write the whole thing out. You can't use EDTA in the name. So you can't say sodium EDTA, even though I use EDTA all the time. But properly, we have to spell the whole thing out. Ethylene diamine tetraacetato, lead or plumbate? It's negative. This is an anion, therefore it's got to be plumbate. And the charge on lead? 2, plus 2, so it'd be Roman numeral 2. Because EDTA is -4, and so this whole thing must be -2. Write the name for this. Tri or tris? Tris, ethylene diamine. Again, you have to spell it all out. It's all one word. So the ligands are named first. Tris, ethylene diamine, chromium or chromate? Chromium. And the charge on chromium? 3. The charge on chromium doesn't have to match the net charge. You know, if I had some anion ligands in there, it won't match. But when we write the Roman numeral, it's the charge on the metal. How about this one? Diamine with 2 M's or 1 M? 2 M's. Silver or argentate? Silver. And silver is just +1, but we're going to write the Roman numeral 1. So this would be diamine, silver 1. Okay, do we write the ligands first in the formula or the metal first in the formula? The metal. So we have square bracket, CO for cobalt, and then we'll just write the ligands in the order. So how many amines? 2. So NH3, 2. And how many aquas? 2 aquas, so H2O, 2. How many bromides? 1. And how many chlorides? And what's the coordination number of this? I didn't ask you that, but it's 6. So we had 6 different ligands on there. Or 6 ligands, I should say, not different. Write the name for this. Cyano or cyanido, either, I don't care. Silver or argentate? Here I care. It's going to be argentate, Roman numeral 1. And so dicyanido or cyanoargentate 1. And then this one would be hexa, aqua, iron or ferrate? Iron, 3. So your quiz on Monday will be similar to this. Some multiple choice, some nomenclature. That's it.
How many questions are on there?
It's not going to be very many questions. This was unusually long. That's why it's a worksheet, and you took it home if you wanted to.
Which experiment are we doing?
We're doing Le Chatelier's experiment. Take a look at the video. I talk about Le Chatelier's principle in the video.
We're going to